Alright, welcome to another draft physics video production, pretty much. Today, we did the overview yesterday. I guess we'll do the underview. I'll attempt to concentrate on the basic mechanism that I'm proposing solves all of the problems, answers all of the questions, dispenses with all the woo and complexity of understanding basic physics, what's really happening. I like to get to magnetism, and this notion, stated by Professor Lewin in this form, that you'll get the Nobel Prize if you find a magnetic monopole. So this idea that there's no charge monopoles in a sense, which is should bother somebody to say that with all of our great science, we can't somehow take find a machine that can separate yin from yang or something. It just doesn't make much sense that this thing could exist called a dipole, and there's no such thing as the bits that make it up. So let's understand Maxwell was in the 1800s, before the discovery of electrons and protons. So he sort of had a reason not to think, in terms of elemental bits and function. So there's some reason for him to say there's no such thing, but there's no reason for a modern scientist not to realize that the electron and the proton have every single, I can't think of a single attribute they have that is in any way unlike what a monopole would have. So however you would describe one of the poles of a magnet, whatever the definition of its function would be, it would be identical to either an electron or a proton, in the sense that it's basically just saying there's two charges and you put them close together and you have a dipole. So if you take an electron, a charge, and you take the proton as a charge, and just understand they have this opposite polarity, plus and a minus, and minus, and it's a real difference. It's not like plus is less of something and minus is more of something, less of something, and plus is more of something. They're clearly distinctly different, distinctly opposite in how they function, in the sense that they behave oppositely towards each other. So if I put another electron here, they repel and they attract to the proton. So there's an inverse relationship, a perfectly inverse relationship, and it can be understood that if I was to actually take an electron and a proton and put them next to each other, without them crashing into each other, that I would in fact have something that would behave exactly like a magnet. So if I made another pair of these electron proton things, I would have exactly what I have when I have a magnetic reaction. I would have very strong attraction, and if I inverted it, I'd have very strong repulsion in this circumstance, because the protons would repel and the electrons would repel. And if I inverted it, I'd have very strong attraction. So it fits exactly what the function is. So just because Maxwell didn't know of the existence of these elemental bits, science is clinging to his edict that monopoles can't exist when clearly they exist. All right. So anyway, so what's the argument I'm making is that this is really simple, and so the only way you can make this happen, I'm arguing a simple argument, is that you really can't do it, unless you do create another mechanism. You can't just have red and black. Okay, you have to have some medium that knows the difference, that can make the difference. So you can't have one kind of force on the outside, okay, that makes that can tell the difference between electrons and protons. You can't just bend the space in one direction and get this reaction. You need some way to bend space in both directions. So if bent space was the answer, you'd need some way to compress space too. So you'd have to have two pieces to that puzzle, two elements, to create this inverse relationship. So I don't want to go into a huge proof that there's no other way to do it, but there's really no other way to do it. You really have to create two forces. So anyway, so that's the first two in the physical equation, is understanding that the universe is just these elements of stuff. Okay, and I could draw them, I'll draw them going numerous directions just for your edification. And there's an equal amount of that stuff. So that's starting a universe with just saying cosmic background radiation. You know, all you have is, you have a universe that's just full of little bits, little BBs, let's say. I'm going to turn them into swimmers and then into rowers. But anyway, and they move they move the speed of light, and they're all the same. And that's where you start. You just start with that. A box, a universe full of whatever, some preposterously huge number of this stuff, a density of it. And as I've pointed out, from any location in space then, anything will sense the universe. That is, they will interact with a universe where BBs hit them. And all the BBs that hit them will be coming from all kinds of directions, you know, into 3 dimensions. And it will appear, from their perspective, that the whole universe is looking at them. That there really isn't any other universe except this universe pushing on them or hitting them. And they're getting hit by as many BBs forward as they are getting hit by BBs backwards, if you created a solid thing in here. So that's basically the point. So first, if you can just believe this, just like cosmic background radiation, there's a bunch of photons, a bunch of clumps of matter, you know, little clumps, and all I'm arguing is that these clumps, okay, if I have them in random places, okay, we don't have machines that can detect them. They're not randomly sized, so I don't want to give the wrong impression. All the same size, but if you have a stream of them going this way, you know, you'd have another stream going this way. So BBs are hitting me from both directions, but if they don't have any coherent arrangement, we don't have a machine that can detect that, except gravity. We can watch gravity doing exactly that. But we don't have any way to detect it in any formal way. But if they come in precise, regular intervals, we can create a device that has a sympathetic frequency. That is, it creates a sympathetic, say a pendulum swing, okay, that just happens to be the same length as this length. And so we can create a system that can detect this, because this will hit the pendulum in the right way each time, and it'll add energy to our pendulum. So if it's the right frequency, it adds energy to our pendulum, and we can tell something's happening because our pendulum is swinging more. And so we can detect certain forms of this radiation. Alright, so I don't know if I want to go into... Okay, so the other form this stuff can be in is when we have magnetism. And the argument would be is that all magnets are doing, as a function, is converting a mixed field of energy. Okay, so energy's moving in this direction, let's say, the little BBs. There's equal BBs coming from the other way, but we're not talking about them right now. And it's just a randomized amount of this stuff. And when it encounters a magnet, as I've pointed out, and a magnet would just be, you could think of the magnet as just being a big proton and a big electron. But the magnet itself is made out of little tiny magnets, okay, you know, just stacked on top of each other. Alright, and the idea is that this red energy will reflect off of the red end, and the red energy will go, well, I might as well keep this red, the red energy will go out the black end. Alright, and the inverse happens. The black energy reflects, wrong way, reflects off the black end, and the black energy gets diverted out of the red end. So functionally, now you have a north and a south in the sense you have all black stuff coming out of one end. I drew this the wrong way. This turn should be this way, and this turn should be that way. So this is the wrong way. Sorry, I mean, it's live performance is a little bit dangerous. So the idea is the black goes into the red and comes out the black end. All right, and the red goes into the black and comes out the red end. So what do you end up with? You end up with the reflected black, right? So your final magnet after the force interacts with it. So it's sitting in the field. It's just sitting in a field of this stuff, BBs, coming from all directions. They're coming in all different directions. And what are they doing? Well, all the black stuff is reflecting off of this. Okay, and all the red is reflecting off of this. Alright, plus all the red that went into the black is also coming out this end. Alright, and all the black that went into the red is coming out this end. So what would you see if you're sitting there looking at this object in space, this thing that was made just by existing in the space and doing those simple functions, two simple functions, either a reflection or a diversion. So with those two simple functions, what do you have? You have this completely different arrangement again. And again, it's kind of obvious that if I put a black thing here, okay, that it's going to be highly reflective because black reflects black perfectly. So all the energy gets trapped here, goes back and forth. The closer they get, the more interactions, quite obviously. It perfectly fits the inverse square law. It perfectly, well, in this case, the two forces are mixing, so it's actually the R cubed law. But if we just cut the monopole, it's the inverse square law. It perfectly fits the evidence. And it's this simple. I mean, this is all you have to have is these two kinds of force, two kinds of matter, and two kinds of interactions. And that's it. That's all you need. And it explains perfectly the function. It explains why the magnets turn. You know, if I put this magnet here in this opposite direction, you know, I mean the same polarity, you can understand that this end is going to push this end away. This end's going to push this end away, okay? And in a sense, this end is now going to be attractive. I didn't really explain the attractive part. It is going to be attracted to that end, and this black end is going to be attracted to this end. And now it's going to be attracted because, as I pointed out, everything that this black end, all the black doesn't give the magnet any momentum. It just converts the force into a new direction. So it essentially goes through the object. It doesn't affect it. And so there's no reflections happening between black and red. There's nothing gets reflected. All the black energy goes out of the red, all the red energy goes out of the black, and you end up with nothing reflecting. So there's low pressure between these two, and there's low pressure between these two, and obviously high pressure this way. So the magnet's going to turn. It's going to twist towards the low pressure. This is pushing up, this is pushing towards, and it's just going to turn and flip. So it has the opposite polarity, which will mean they'll attract, because they'll create all low pressure. I mean, you can sort of, I don't probably have to explain that to you, but if they're oppositely poled, you can see that all the black energy goes out, all the red energy goes out, and you know, all you end up with, well, obviously this black energy goes this way. A few details, you do have to be careful. I mean, even though it's simple, it's still, you still got to stack the ABC blocks in the right order. But anyway, all right, so I don't want to get extensively on that. So I'm just saying the evidence that this is the right answer is solid in the sense that it fits what we see. And as I'm pointing out, I don't think anybody can give me a rational explanation for how the electron and proton fail to have an equal sign. Okay, electron, proton, okay, equal monopole. Okay, there's no way to miss that. It's I haven't seen it. Nobody's commented. Nobody's said anything. How does an electron and a proton fail to meet the definition of the magnetic monopole? They don't fail. I mean, it was in Maxwell's own drawings. I mean, Maxwell drew these drawings of charge, and he would draw charges next to each other, and he would draw the fact that they are acting as if they were a dipole, as if they were a magnet. He just didn't have anything to go, oh yeah, it's a proton and that's an electron. He didn't have the ability to see inside the atom well enough to realize it was made of these elemental things that had these charged components. He thought charge was something big objects had. He didn't think of it in terms of little objects. All right. So, let's move on. That's the basic thing. So all you have is forces. All right. So as I pointed out, the force by itself is real momentum. The force when it's at a frequency, okay, is something special. Photons, the electromagnetic spectrum. We can detect some of this stuff. All right. We don't have a machine that can detect one of these, but we do have a machine that can detect these in the right sequence. And depending on how off the sequence is, we can detect it even when it's broken. So even when the frequency is this plus a little closer one plus a little shorter one plus a longer one, we'd still be able to detect that because it has enough energy to kick an electron. So we can detect mixed radiations, but we can't tune to them as a frequency, but we can know they were there because we can read the signature of high energy. So if something has enough energy, enough frequency, it's happening often enough, it doesn't matter because it creates effects we can detect. And it's all about creating an effect. We can't see this stuff because we can only see stuff like matter. We can only watch matter move. We can't watch a photon move a little bit. And then in magnetism, it's just understanding that the force comes into two types, okay, and that we can segregate those two types, and that's magnetism. So the force has two forms in nature. Magnetism, or the electromagnetic spectrum, is black energy, okay, the black force, the electron force, because we're just watching what it does to electrons, moves them. It gives electrons momentum. The red force can't give an electron momentum. The black force can. So that's why photons are relevant, and they're always made of black energy. This black energy gives electrons momentum. And the momentum that's given by red energy to protons is not really visible because of the relationship protons have in the nucleus, which is they're stacked very close together because they have a binding neutron that contains an electron, and so they're bound very close to each other, so they're very hard to break loose, where it's really easy to break electrons loose because they're way out here and they can be kicked much easier because they're not in this bound relationship. They don't have a proton between them, so the electrons can get really close. So anyway, it's probably more detail than you're able to absorb, but whatever. All right, so if we could agree that it's plausible that the universe could be full of cosmic background radiation, that is radiation that's coming from the universe, so the universe is just a sea of radiation, so you just start with the idea that you have this stuff. Should put that higher. Well, I can always go higher. I can put one up here, and I can put one over there. And so we'll start with just that. Alright, now let's, and as pointed out, if I put a piece of matter in there, it's going to get this impression that the whole universe is heading right for it. So that's just a physical fact of the randomness, is that it will feel like pressure. Stuff is going to be pushing you from all directions, hitting you, interacting with you by imposing. And it's imposing, in the case of common forces, it's imposing momentum. All right, so so we just start with that idea. Then we can say that an electron, okay, is an elemental form of matter, fundamental, made of this, but it's made of this in some kind of this in a new form. And the new form would be is that it contains, it's like a boat. Okay, so think of these little pieces of energy or momentum now as swimmers. And when swimmers get into boats, okay, they become rowers. And so an electron needs 5 of them to make my point. Okay, so an electron is basically just seats in a boat, but it's more precisely they're filled. So an event happens in the universe of some type, and electrons are created by essentially compressing this into a form where it is arranged. That is, it's all black pieces. So all black pieces get into a boat, all right, and it may be just by randomness this happens, and ones that are too few seats, like if I made a small electron and only had 3 seats, there wouldn't be enough durability for the vibrations that come in. So it's like if you don't have enough of a cushion or a buffer, your seats would get destroyed, because the universe would come in this way with enough energy to fill all the seats and pull all these seats right out of the electron. But the idea is the electron has this in all directions inside of it, in all dimensions. And these seats. So the boats are round, spherical, and there's seats in all directions, and there's a certain number. In the case of electrons, this odd number works, 5, let's say, just for the example. It's probably 5,000 or 50,000, but anyway, there's a certain number of seats in the boat. And the idea, simple idea is that when something from the outside hits black energy, it takes the seat occupied in that dimension and kicks out somebody going the opposite direction. So if there's a guy going this way in this row, this guy will kick him out of his seat, take his seat inside the boat, and be a rower this way, and he'll release the other rower that was in that seat, and he becomes the free swimmer. And so there's your equal but opposite reaction, to satisfy Newton's laws. And the boat changes. So essentially, electrons are a kind of battery. They have stored inside of them a condition of energy, potential. So if there's an electron that starts off with, say, 5 rowers going this way, and only 1 rower, or 0 rowers going that way. So if there's an electron that starts that way in the universe, you could surmise that there's probably another boat somewhere where it's doing exactly the opposite. There's 5 going that way and 0 going this way. Or you could surmise that there's swimmers in the sea, that is, force ready to hit something, ready to get into a boat in the sea. So there's always a proportionality. So if something's moving in one part of the universe, it's going this way, there's a force, or there's a boat going that way somewhere else in the universe. That's your conservation. Alright, so I'll redraw this. Alright, so we start off with just the force. Now we have this electron that has an odd number of seats. So let's understand, with an odd number of seats, it can only have 3 to 2 or 2 to 3. It can never have 3 and 3 or 2 and 2. So it can never have an equal amount of momentum inside its boat rowers. It's always got 3 going that way and 2 going that way, or 4 going that way and 1 going that way, or 5 and 0, however you want to look at it. And so it always has to go this way, or it has to go that way. It has to be doing one of those any 1 second. And likewise, it has to be going this way, or it has to be going that way every second, and in and out. So in all the 3 dimensions, it has momentum. And that's why when you hit it with a force, and I add extra momentum in this direction, and I eject the swimmer, the electron doesn't go that way. It goes a little bit the way it was already going, okay? Because these seats, these other directions, are going to decide what its momentum is. And you're just adding to a composite, and so it'll have a net movement. It'll have a net product, which will be a vector in some direction that won't be exactly the direction where that went in. But it's always moving is the consequence. It's always going somewhere. It's just that in a field that's equally balanced, that is, as many heads on tails, you're getting hit from both sides fairly evenly. Any 1 second you have a little more this way, next second you have a little more that way. So the electron, if it's traveling, if it has some extra momentum, 3 or 4 imbalances here, it just basically goes through space very, it doesn't take straight lines. But if you hit it with enough force, obviously, you can have a very high bias in one of these dimensions. So this dimension could be, 400 to 4 or something. So it's got a lot of momentum in this dimension. So the wobble gets smaller and smaller the faster it's going, because there's less dilution by the other sides, because this is such a heavy imbalance. So as the electron is more stationary, it's wobbling the most, and as you move it, it wobbles a little less. And that's perfectly what we see the electron do in the real world. Even in electricity, this kind of confuses people sometimes, because the electron is moving essentially faster when it's not being electrified. And when you put current through the wire, the electron appears to be moving slower. Okay, well, what we're measuring isn't its actual capturing of distance. We're only measuring how much, we're measuring this as movement. So it's doing a lot of this when it's stationary, and when you're moving it, it actually appears to be moving slower, only because you've taken out so much of this stuff that you were confusing with actual motion in a direction. I mean, backward and forward is real movement. I mean, going up and going back down and going back up and going back down, these are all real velocities, real accelerations, even though you don't go anywhere. You're not capturing any distance. It would still can look like, or feel like, or be like real movement. I mean, if I did that to you, if I threw you up and down and you weren't going anywhere, you'd still think you were going somewhere. It would feel like you're going somewhere. It would feel like you're on a trip, but you're not. All right. So how much of this do I need to save? I don't know. We'll just say you've got the idea. Okay, so the 2 boats. So if you just understand, I just drew you the black boat. So the red boat's pretty much the same, okay, as the electron boat. So the electron boat is odd. All right, number of seats and in all directions. And then the proton boat is the same boat, fundamentally, except it's got an even number. Okay, so it can have the 0. All right, it can have 1 and 1, or 2 and 2, and 4 and 4, and all of that kind of stuff. So it doesn't have the necessity, where this can only do, that way or that way. This one has the third choice of, that way, 0, or that way. So it's a lot quieter than this boat. This boat's always jiggling, where this boat doesn't have to. If you put it in a quiet enough, perfect enough, even enough field, it'll move very little. very little vibration. All right, so that's what you got. You got two boats. I mean, you got two kinds of swimmers, red shirts, black shirts. You got two kinds of boats, black boat, red boat. And you got two rules. When a red swimmer goes into a black boat, he just gets deflected. When a black swimmer goes into the boat, he makes an exchange with the boat. An opposite swimmer leaves, and the boat moves in that direction or it changes its direction in that, it slows down going the wrong way, or it speeds up going the way the swimmer added. But momentum is imposed. So you have the reflection and you have momentum. The other reaction, you have just a change in where the force was going. So it was heading right for somebody over here. It doesn't hit that somebody. Instead, it goes over here and hits somebody who wasn't going to get hit. And so the universe is fundamentally changed by this changing of the direction of the force, the swimmer. He was getting in that boat. He can't get to it now. So he's going to end up in this boat. And that changes things. Who gets in what boat? All right, so with those two functions, really, two kinds of force, two kinds of boats, and then you just play it out. You just say, what happens if I have a red boat next to a black boat, as pointed out. So let's say if I have two black boats and they get close to each other, you get the idea that, well, a swimmer jumps out of this, a swimmer jumps in this boat, and then that means a swimmer jumps out. Okay, that means it happens here, and the same thing ends up happening. The swimmer jumps in this boat, this swimmer jumps out, so this one keeps getting arrows in, right? That's all this one will see is the reflections. The every time an exchange happens here, it means this gets hit. He gets somebody coming right for him. This guy won't see this one leaving. He doesn't care about that. But he'll see all these others coming. He'll see the consequence of this one leaving. And the consequence when there's another boat is that it's coming right back. It's heading right for you. So every bullet you fire ends up just coming right back for you. And you have this perpetual reaction. So you have almost theoretically, you change the energy to infinity as you bring these closer and closer together. Obviously there would be some sort of limit, but it gets a tremendous amount of force because of the reflection. So, and both of these boats are getting momentum because this is black force, so both of them are going to move away from each other into the force. Now, what's the consequence of moving into the force, into the field? Well, the field has swimmers in it, and obviously in the direction you're moving, you're going to hit more swimmers than come in. Should draw that separately. Yeah, I should. You absorb that, right? I don't have to leave images up forever. So the idea is that, so once you have a boat that has a bias in it, it has 3 or 5 imbalances in different directions, and so it has a momentum in, say, this direction, a certain amount of imbalance, and it's moving this electron into the field, and the field is all mixed. Let's say there's nothing else in the environment. Well, this momentum isn't going to last too long, because the idea is going to be is he's heading into more swimmers than are going to catch up to him. So even though he's not going very fast, you don't have to go very fast. Any speed at all will change the probability of hitting a swimmer. So if I have any speed in a direction, the fact is I made this more probable, and I made this less probable. It's reversal of signs, but I'm just saying it's less probable somebody's going to jump in the back of your boat, and more probable somebody's going to hit you in the front of your boat when your boat's moving. You hit more water in front of you than behind you. Even if the water was moving, that's just a fact. So you'll collect more swimmers that'll make more interactions with these swimmers, and each interaction, as stated, reduces your momentum. So each time somebody jumps in going this way, I'll do it in red just to illustrate the jumping in. So each time somebody jumps in this way, you're going to absorb momentum that way. So if you're going 40 miles an hour this way, you're in a couple of milliseconds, you'll be going 30 miles an hour. And a couple of milliseconds later, you go 20 miles an hour, and 10 and 0. So it's going to eat up any kind of momentum you have. Is going to disappear fairly rapidly. I don't know. That's a relative term. We don't know how rapidly exactly or precisely. Well, we sort of do. They sort of do know how fast things decay in terms of how fast an electron. So when they show pictures in cloud chambers of electrons spiraling, to death, what that really is their deceleration. They start decelerating in the field, and this is them basically stopping moving, more than being attracted to anything, losing their velocity. So to maintain an electron, you have to keep hitting it with more swimmers, okay, more force, more photons, more energy, more magnetism, more whatever you want to call it. In accelerators, they use voltage, a charge differential, which just means they create a circumstance where there's a high amount of this black energy coming and very little of that red energy, and create a potential, and that keeps pushing the electron. But they have to keep adding more and more force to get more and more velocity out of the electron, because it's heading into more and more force. The more speed you give it, the more of this stuff it hits. The more it slows it down. So you're fighting the drag, and so it takes more and more and more energy to get it to go faster and faster and faster, because you're plowing into more and more opposing swimmers. So that perfectly fits what we see in the real world in terms of what electrons and protons do. I've explained in the previous video how matter requires velocity, that is atomic matter, so I don't know if I need to do that again. This sort of explains all of that. So it's just the inverse for the red bits, like I said, except they're not as they also will drag, they'll lose speed, but just the only thing really that's the difference is the fact that they don't have to be perpetually moving as much as electrons do, just because of this odd even thing. Alright, so you have the two forces, you have the two functional bits of matter that explain charge, and explain what charge is and how it functions. Essentially, charge is just reflecting or not reflecting. It's as if these two things have exactly opposite mirrors in front of them, and they reflect the world in an opposite manner. If this one reflects blue, this one reflects red. If this one reflects pink, this one, the inverse kind of colors. So you see it, the opposites. One reflects from the waist up, one reflects from the waist down. There's just nothing consistent about it. It's exactly the opposite images, the opposite effects. And so then we're back to the monopole. So I'll do a little bit on the structure of a magnet, just so it's understood. Alright, so we can leave that. So people like the Ken Wheeler types and the rest, point out the obvious, which is, if you break a magnet in half, you take a big magnet and you break it in half, you end up with two, small magnets. Well, I'll draw them this way. Doesn't really matter what their orientation is, but you'd end up with two magnets. This part, like if I broke it right here, I don't end up with a black and a red. I don't end up with a monopole. I end up with two new magnets that are, I really should draw it the same way, that end up doing exactly what the first magnet is they turn into magnets. I end up with this piece ending up being a magnet, and the bottom piece ending up being a magnet, just like the first magnet. So I just create a smaller version of the magnet by breaking this, and I could go on and on and on. Now the point would be, is if you went on and on and on and on, and you got to the atom, you'd realize that that's the original dipole. The atom is the fundamental, the electron, the proton, That's the fundamental magnet. And if I broke that one, I would end up with the monopoles. I'd end up with the electron and the proton. And those are the original source monopoles. Okay, so the way that's constructed is you can sort of, you could probably deduce this yourself, but I'll do it for you. All right, so it does reduce to an elemental bit that is the source of the function. And so the idea is that the regular magnet is really made out of a composite of a bunch of little magnets. It could take me years to draw, but let's just try to do it efficiently. So you can get the idea that if I'm going to be staggering these magnets, because they won't stick to each other black on black and red on red. They only stick to each other black on red. So in the magnet, all right, I put the red bit here, I'll put a red bit here, and I know a red bit has to go here, and I know a red bit has to go here, and I know a red bit has to go here, and then I can add some, I know a black bit has to go here, and I know a black bit has to go here, and I know a black bit has to go here. So you get the idea that you end up rather quickly creating, well, I already have flaws in that. Frankly, I made a mistake somewhere. Well, anyway, you get the idea. Checkerboard, all right? And but there is a real orientation in terms of the atoms are real. Okay, so they're, although it looks like it's a magnet going two different ways, like you could look at it this way, the magnet's north-south, or it's north-south, or, you know, north-south. You can make it look like it's oriented anyway. The atoms have a real orientation. So these magnets in their atomic function have a direction. Like these two are connected, and these two are connected, and these two are well, I did it the wrong way again. Alright, so that one's connected, this two are connected, these two are connected. Alright, so that's the part you have to see, is that they're staggered magnets. So this is a magnet, and this is the magnet, and this is the magnet. So the magnets are arranged staggered from each other, so they stick to each other. But these are the real magnets. So these are the real bits that are functioning. Okay, they're the real atoms. The real atoms are doing this. They're lining up staggered to each other. You know, if the black's here, in the next row the black is one down. In the next row the black is one down. They're always staggered, so they can stick to each other. Alright, and so the consequences, you have to understand that, yes, so that's why when the energy goes in, the black energy hits the red, it goes up, because that's how the proton deflects it. So the proton is, it gets hit by the energy, and the proton sends the energy this way, the direction of the electron, let's say. And so the energy goes that way, it hits the electron, let's say, and moves it and all that kind of stuff, and that hits the other next, the force ends up jumping out of that boat eventually. It goes up and hits the next proton sends it left, and then it goes back up right. So the whole point is that the black energy, no matter where it goes in, to a red, that is wherever it hits a proton, it ends up going up. Okay, it's going upstream eventually, because the energy won't go proton to proton. The energy will always get diverted, and the diversion will have a probability of ending up always up. So even if it goes in and it goes up and it goes sideways and it goes sideways, and the probability is that it'll always end up heading that way. And any red energy that goes in will have a high probability of going that way, in terms that it'll cause momentum in that direction. And momentum means that an electron or a proton pushes against each other. An electron gets a proton gets closer to a proton, or an electron, more importantly, more likely, an electron gets closer to an electron, which means it puts swimmers in its boat and moves the other electron. So it all ends up moving, and that's how the mechanism works, is that the magnet is yes, you can break this magnet at any location, but what you'll be breaking is an uneven line. Okay, so you can break it, but what you'll get at the bottom of the or the top of the electron is this kind of configuration. Okay, and these would be the red bits here for the other magnet. So you'll just have, oh, I put them in the wrong place again. Yeah, way to go, Gary. Alright, so you have the black ones, and the next row of black ones will be in here. Okay, that way. And it'll be red ones here. So the red will be here next to the black. Red one here next to the black. Red one here next to the black. So from the outside world, you know, looking at this side of the magnet, all you're going to see is black. You don't have any access to the red bits, you know, because that's where the magnet's going to break. The magnet's going to break on full atoms. It's not going to break a half an atom. It's going to break on the full atoms. This is a full atom. This is a full atom. You know, this is a full atom. This is a full atom. This is a full atom. And so it breaks staggered. And the stagger means that it breaks on one side, all electron facing down, and on the other side it's going to be exactly the opposite. It's going to be the red bits sticking up. Okay, and so you'll make two new magnets, quite obviously. This one will have the red head, the red part will be facing up on this one. You know, kind of obvious. So the one you broke here, the bottom one, will break red, black, and the top one will break red, black. Red on top, black on the bottom. So it'll be just like the original magnet, which started off red and black. Okay, you could argue, right? And they'll look like you just made two magnets, but as you can understand, you did it this way, and they're really opposite magnets. Okay, I think you can see most of that, right? Well, hopefully you did. So anyway, so that explains how a magnet works. A magnet doesn't create any energy, doesn't do anything. All it does is filter the energy that comes in. Everything just filters. Electrons filter. They reflect black, they divert red. It's a filter. Protons just filter. And so all you have to do is believe in this energy. And it's already there. I mean, we already have evidence of it in the cosmic background radiation. Now, we detect the cosmic background radiation because it comes at a specific frequency. So as I pointed out before, we can't sense gravity any other way than to drop things. We don't really have any other way to sense the force. And I would argue it's a real force, just like anything else that causes motion. So you can sort of understand that there could be a whole bunch of this energy, and it's simply in forms that we can't see. You know, we just can't detect it. Now, I would argue that the experiments with polarizing filters kind of give us a clue to the existence of that energy, because a polarizing filter, when we send light through it, and it kind of breaks the light that goes through. So the sequence of the light has a specific sequence, as I pointed out. It goes through the filter, and one of these bits will get hit because it's a little bit off this perfect line. So it'll go into this bit of the filter. And when it does, it gets its phase changed. So now this one is here instead of here. I mean here instead of here. Okay. And so now what comes out is this wrong pattern, in the sense that you got two bits here, and then you got a bit here and here. So the frequency's been broken. We can't detect that. So if you do that to a photon, we can't detect it. Now it has the same amount of energy. It's the same amount. It's all cannonballs. I mean, it can do real things when it hits something in the real world. It just can't do what electrons need to do, which is to hit it consistently. See, an electron's tipping. An electron's requiring you to hit it in a sequence where it's wobbling, and you have to hit it constructively. That means you have to hit it when it's moving, tipping this way. If you hit it when it's tipping this way, you lose any effect you have. You have to constructively add to its swing. So when it's swinging this way, you hit it again, and that makes it swing even further and further and further. So you're tipping essentially the electron. And you can't tip it with this frequency because that lets it spring back. This open space lets this spring way back here again. So then you got to start all over. And this photon isn't going to be long enough to start all over. So you're out of luck. Okay. But the point is this filter, okay, this polarizing filter doesn't get hot. And we know that photons going into things should make them hot. So the photons aren't getting absorbed. They're not staying in the filter. The energy isn't flying around inside the filter creating heat. Okay? No, the photon went through the filter. The energy of the photon went through the filter. So we already have examples of, we saw the photon here, we could see it, in the sense that we knew the energy's there going in. We can measure it. We can hit a brick wall and we can say how much energy is going in. But when it goes through this filter, it's converting the energy. So we don't see the energy here. It's not there. No energy, no heat. Hot, no. Hot, not. Hot, not. So therefore the energy has to be out here. It had to go through the filter, yet we can't detect it as a photon. We put a photo detector here. We can't detect that photon because that photon's broken. And it's broken in just a trivial way, where yes, it's all still there, and all you need to do maybe is put it through another filter. See, the energy's still there. It's just in the wrong phase. Wrong location, Gary. Alright, the phase is broken. And so we can put through another filter that will cause another phase shift to these. So the ones down here get phase shifted. And that'll put this one back where he belongs. And then you'll have a photon again. So it's the 3 filter test in light. You put one filter and the other filter is the opposite direction. And this filter fixes the photons. Well, it fixes them in this process. And now you can see this photon. So you see it when it's got its frequency, because we can only detect this energy when it works with our electronic device that's got a pendulum swing, and the pendulum has to be hit each time. And if you don't hit it, you won't add energy to it, and we can't detect it. So it has to have the frequency. If the frequency is broken, we can't detect it. Doesn't mean the energy is not there, just means we can't see it. We can't make it do what we need it to do for us to see it. And what we need it to do is we need to hit an electron just the right way. It has to have all the components, all 5 or all 6 components have to be there and have to be in the right sequence. And if one is missing, you got to start over. And it all fits. This is how the universe works. It doesn't work with woo and waves or any of that stuff. Waves are an emergent property. Waves happen when you send a whole bunch of photons. Okay, you say, I got a million soldiers over here, and so I'm going to shoot them out. And I open doors and they fly out. Okay, so I open 50,000 doors and 50,000 soldiers pop out. Right? Now that could look like a wave. It's just 50,000 soldiers. And then I open the door again, another 50,000. And I do it exactly, 1 second difference between each time I open the door. And that's what I'll end up with, is 50,000 soldiers, okay, coming out. Now, in real physics, these things usually are diverging. That means they're on divergent paths. So they're spreading as they go through space. So they're not moving parallel like this. That's like a laser beam. They're moving, they're close together where they start, and then they get further apart, and then they get further apart, and then they get further apart with distance by the inverse square law in both dimensions. But okay, so this, you could see this as a wave. It looks wavy. Okay, it's got the concept. It's like an ocean wave. This could be thought of as a hump. There's a big bunch of stuff, and then there's no stuff, and then there's a big bunch of stuff, and then there's no stuff, and there's a big bunch of stuff. Yeah, you could draw it as a wave, but that's all you're doing. You're drawing it as a wave. That's like what an oscilloscope does. An oscilloscope sees this, and it turns it into this little wavy line. But that's not what it detected. It detected energy. Okay, it didn't detect I see some of the soldiers, then I see, no, I'm starting to see less, I'm less and less, then I see more and more. No, it's not really doing that. It sees all of them at once. Okay, and it interprets it for you because it's tracing. Okay, it can't, when it's tracing, it can't help but make this look like a peak, a triangle or a sine wave or anything else, because it's a moving trace. All right, I don't want to have to explain every detail. So anyway, so that's the inside. The inside is all you need to explain everything, every phenomenon in the universe, is to understand there's two kinds of force, there's two kinds of matter, fundamental element matter. Maybe there's other configurations. Maybe there's forms of, say when they say there's a positron or some other thing, well, they see those things in accelerators in other places, but they're just illusions, in the sense that when you smash these things at high velocities, you could understand, okay, that there's going to be a bunch of compressed force, especially if electrons hit electrons. But even if you smash protons into protons, see, there's some little bit of energy that comes into the proton that's black, and it takes a turn and hits this electron. It doesn't reflect back again, right? The electron reflects it, and it comes back out again. So there's always some pressure between even electrons and protons, some little bit of pressure. And so they test that, and they push against it. But they don't really destroy these particles. What they do is compress them. So they hit electrons essentially against electrons, or protons against a proton. And they create a incredibly high pressure here, because they get them so close that these vibrations happen at a very fast rate. And so they can create very fast frequencies of photons that end up coming out of that. And they're basically calling that a new particle, when it's really just energy. It's not a particle. It's not an elemental material bit. Those things are just clumps of energy. They're just a group of swimmers. In a group of swimmers, okay, rowers, just freely going. So if I group a bunch, kind of smash them together, that could look like a boat. Okay, it can have the same basic function as a boat, but it's not a boat. All right. So you have two kinds of matter, fundamentally. There's only the electron. You have two things. You have the positive charge and you have the negative charge. You have the positive boat and the negative boat. Basically, it's really all there really is. You got the electrons and you got protons, and that's what the universe runs on. And then you have two interactions. So you have the diversion with no momentum, and you have the I have to draw it with black, and you have the it's not drawing very well, and you have the reflection, okay, off the electron that causes momentum. All right, the inverse for the proton. So that's all there is. Two kinds of force, two kinds of boat, and two kinds of interaction with the boat: deflection or reflection, deflection or reflection with momentum. All right, I can't really make it any simpler, and there really hasn't been any challenge, right? There's nothing in the comment section to indicate anybody has any counter argument of any kind. Why does this not work when it works perfectly? And it explains magnetism perfectly. Every bit of it is explained with just these simple functions. Two kinds of force, two kinds of charge, two kinds of interactions. That's it. I can't make you reasonable. This is the reasonable explanation for how our physical universe works. Bent space and virtual photons and entanglement and all this other woo is just that. It's a religion. It isn't logical. It doesn't fit the evidence. Its inconsistencies are all over the place. Its paradoxes are all over the place. It doesn't work. This does. And it's so much simpler. I mean, a million times simpler. I mean, look, I'm just, what can I say? I can't make you reasonable. You don't think in hindsight this is going to look even worse than the evolution argument? You know, that no matter how much evidence Darwin compiled, there's people who are saying that can't be. It can't be. I ain't related to monkeys. Yeah, that's the best they could do. So what is your argument? I mean, what's the counter argument? I mean, how much of a dumb Christian do you want to look like? Because that's what physics looks like. It looks that retarded to sit there and obstinately say there can't be any explanation. Nobody can do it. It can't be done. You can't find magnetic monopoles. You should get the Nobel Prize for figuring out there's they haven't even tried to define what a monopole would look like. Because if they did, like I said, it would fit electrons and protons so perfectly that they couldn't miss the obvious. So somebody who wants to disagree, just point out to me how protons and electrons aren't perfect replacements for whatever the non-existent monopoles would be. How I could put a proton in as the fake monopole, and how you'd be able to tell. Because you wouldn't be able to tell, because they're clearly the monopoles. So why do you keep preaching this nonsense that there's no monopoles when they're just that obvious? Okay, well, I can't, like I said, I can't make you reasonable. You know, I'm stuck in this position where, oh, explain your physics. Well, what's the point if I'm explaining it to people who are unreasonable? And frankly, that's all I see is an unreasonable resistance to the simple truth. Yeah. Okay. So, till the next time. Like I said, it's on you. I mean, you know, I'm just saying you're gonna make your clan, whatever it is, of physicists, of intellectual, of whatever. You're all gonna just look like assholes and idiots in hindsight, because I spelled it out for you. You haven't challenged it with anything. Yeah,